Okay, so the recording has started. So good morning to all of you once again. I hope my screen is still visible. Just confirm it once more.
Yes, sir.
Okay, thank you. So in yesterday's class, we have introduced the concept of like this Carnot map, how to use this Carnot map, and from this Carnot map, we have seen what is the process for minimizing a particular Boolean function. Right? So this is an two variable Carnot map. So that's why we have four blocks. It is 2 to the power 2. It is a three variable Carnot map. As you can see clearly from here, it is x, y, z. So we are expecting here 2 to the power 3, that is 8 blocks, right? And we have seen the how to how to number these blocks, right? For example, if there are two variables, then you have to remember it is 0, 0, 0, 1, 1, 1, 1, 0. There should be only one change from like between this neighboring boxes, right? Only from here you can see only this 0 has changed to 1. From here to here you can see only this 0 has now changed to 1, right? The other one should be fixed. Same thing you can also observe from here, right? If it is a four variable Carnot map, then the same logic will also apply, okay, for this side as well. Okay, then let us take today one example from this four variable Carnot map, and then we'll see. So say a function has been given like this: a bar, b bar, c bar, d, a bar, b bar, c bar, d bar, a bar, b bar, c, d bar, a b bar, c, d bar, a bar, b, c, d bar, a b bar, c bar, d, plus a b bar, c bar, d bar. All right. So as it is clear from this expression itself that there are four variables a, b, c, d, right? So it will be a four variable Carnot map. So four variable Carnot map, total number of boxes would be 2 to the power 4, that is 16, right? So let us draw that. So it is a, b, c, and d, right? So here it is AB, and in this side it is CD is this side and AB is on this side. So for AB again it is 0, 0, 0, 1. Remember it will be 1, 1. It is 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Right? Now put the put the number ones here. Right? So it is A bar, B bar. So it is 0, 0, 0, 1. So it is 1. So 1 means this one, right? This is 0, this is 1. So here we should put here 1, right? You are getting this point, right? This is 0, 0, 0, 1. So that means 0, 0, 0, 1 means basically 1. So 0, 0, 0, 1. So here we should put 1. Now for the next term, it is A bar, B bar, C bar, D bar. So it's all zeros, right? 0, 0, 0, 0, all zeros. So here, so here we should put 1, right? So now here for this term, it is 0, 0, 1, 0. So that means it is 2. So it is 0, 1, 2, 3. Remember this counting? Also, you can take it from here like this 0, 0, 1, 0. So for this, we should put here 1. Now for the next term, A, B bar, that is 1, 0, 1, 0. So 1, 0, 1, 0. See this 1, 0, 1, 0. So here 1, 1. Now for this term, it is 0, 1, 1, 0. 0, 1, 1, 0. So here 1. Now for this term, it is 1, 0, 0, 1. 1, 0, 0, 1. Right? Now for this remaining term, that is 1, 0, 0, 0. This is 1, 0, 0, 0 here. So you can see here 1, 2, 3, 4, 5, 6, 7 terms. 1, 2, 3, 4, 5, 6, 7. Right? We have put 7 once. Right? Now we have to start, making the groups. Right? To find the minimized expression. Right? We have to actually minimize this expression. Right? Using Karnaugh map. Okay. So here, see here, these two ones are there, so we can take a block of these two ones. Also, you can take a block of this ones, and also we know that as the Karnaugh map is foldable, so probably we can also take it like this, right? If you fold it in this direction, right? Like if you fold it in this direction and in this direction, then this, yeah, like this two, this side will connect with this side, and you can make a combination of all four ones, right? So that way we have one one group that is like with four ones. So for this, what would be the, okay, let us write as well. So for this, what will be the combination? See here between, so for this between A and B here, A is changing, so A we should neglect, and B is constant at 0. So it should be B bar, right? So it should be B bar. Now here for CD, now C is constant and D is variable. So D you should neglect, and C is constant at 0. So it is C bar. So it is B bar, C bar. Right? Okay. Other thing that we can do, so you can see at this all four corners we have ones. So all four corners ones. Again, Karnaugh map is very foldable from both the sides, right? So that way you can, if you can fold it carefully, so you can actually attach all these corners, right? So that way you can make a like group of all these four, or like all four, these four ones, right? So which will give you a what? So here see, you can see between these two here, A is again changing, B is constant at 0, so it will be B bar, right? And between C and D, C is now changing, D is constant at 0, so it will be D bar, right? Okay, let's see what else we can do from here. So here you can see almost we have covered all the ones except this one, right? So we should cover, we cannot keep this one, left this one, right? We should make a group of, we should make a group, okay, including this one. So if we do so here, so it is
Sir,
one, uh, 1
sir,
minute, it
that
is,
the lower one would also be included, na sir?
lower one is already included na, in this green box.
No, no, in this blue part also, sir.
Mm-hmm. In this
Lower
blue
one
part,
can also be included, na sir?
lower one, then it will be a group of three, na?
Yes, sir. So why we are not taking that, sir?
So we can take only, we can only combine like 2, 4, 8, 16.
Okay,
Okay.
okay, sir. Yes, sir. Got it, sir.
Because if you they see the logic is very pretty simple only. See for this, okay, let me write it. For this blue, what we can write. So for this blue here, A is change, A is constant. A is constant at A is constant at 0, so it will be A bar. And there is only one block for the C and D, so it is C, and C is at 1 and D as 0, so it will be A, C, D bar, right? Now now your friend has asked, like, why we can't take like three ones. First thing is that we can't take these three because, see, what is this? Okay, let me use this one. Okay, what is these two terms? These two terms, huh? What is this term? Can anyone tell in terms of A, B, C, D? It is A, B, 0, 0. So it is A bar, B bar, C, D bar, right? This term is this one. What is this? This is A, B bar, sorry, A bar, B, then C, D bar, isn't it? Right? Like, suppose if you have used the Boolean algebra, then what you could have done? A bar, B bar, C, D bar plus A bar, B bar, C, D bar, right? Okay. Now from here, you could have taken the, this thing common, right? A, C, D bar. You could have taken common from this side. So it will become B bar plus B, right? So it would be A bar, C, D bar, and between like these two, it will become 1. So that's how actually you are getting this thing minimized here, right? So there should be 2 so that you are getting here this term. So, the two, two side by side thing, because there will be only one variable that will change, right? That's how we have numbered our Carnot map, this number, so that there is only one change in the variable. So that's why we have to take side by side, like only one. Okay, and it should be in terms of this 2, 4, 8, and 16 while we were making the groups.
Sir,
Hmm.
we shall not include two already grouped ones again, right? That will make.
Okay, suppose you want to make here, okay, say one more group like this, right?
Yes, sir.
Right, no point. Then you will get some redundant terms because this ones has already been included. So you should remember that you should not left any one. Okay, if there is no one left, if all ones has been included in in one of the group, then it is fine.
Okay.
Okay. Now suppose in some
Sir,
case,
here we have seven ones. So
7 ones.
one of them should be repeated. So will it be redundant or
No,
is it
no. See,
necessary?
this one was left, right? So okay. So for this one, now what you could have done, this one, if you have not included in this, okay. So what else you could have done? So you could have write it B bar C plus B bar D bar, okay, plus this is for these two group, right? Green and red. Okay. For this one, you could have not make this group, but instead you could have written this thing. Okay, but see, this is not the minimized version, because if you still further use the Boolean algebra, then you could have reduced it from further from here to here. So this one, if you are taking a combination with this, then it will get reduced to this one.
So,
Huh.
so over here there was another option in which we could have taken B bar, C bar, and D instead of the red group, because the red group has two of the ones getting already counted in the B bar D bar group.
Mm-hmm.
So, in those cases, is it preferable to take the larger group or
Yes,
to
yes,
try to avoid
yes,
as many overlapped groups?
yes. So that is a very good point actually that you have raised. So when you are grouping, first try to make the group as large as possible. When you make the group as large as possible, then you will get the minimized number of expression. For example, see, for this blue one, right? Okay, for this blue one, right? What we have seen for the here, it is a group of two like two terms, right? So from here, you can see the expression, the minimized expression that is coming out, that is to be A, B, C bar, A, C, D bar. That means the B we are able to eliminate. That is because we have combined these two ones. So only one element has been removed. Now see, for this red one, right? For this red group, see, we have made this group with 4 ones, right? So what you can expect, two variables, right? Or two like among this A, B, C, D will be eliminated. So you can see from this red, what we are getting is this B bar, C bar. Both A and D has been eliminated, right? So like that, if you can make a group of 8 elements, right? Then that would give you only one variable, right? For this type of only either A, B, C, or D. Okay. For example, see this. Suppose you have 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Suppose you have you have ones. Okay, let me use this one. Okay. 1, 1, 1, 1, and okay. Let me not, or maybe yes, some arbitrary ones. Let me write here. Okay. And let me write here other ones. So here 1 1 1 1 1 1 1 1. Okay, now suppose if you have to minimize this, then what you could have done, you could have combined this 4 1 and this 4 1, right? But you know that we could have also done it like this, right? These 4 1s and this 4 1. So when you combine these 4 1s, so that will give you, see what you are getting from here to here. Which variable? It is A is changing, B is constant at 0. So it is B bar, right? And C and between C and D, like everything is changing here. So nothing will come here. So it will only give you this B bar. So you can see if you are combining these 8 elements, if you are able to make a group, then the expression that you are getting, that is only B bar. Now, okay, let me also split it in two ways. Okay, suppose if you have taken this one and you would have taken this one, right? Then for this, what you could have got, this is A bar, B bar, right? And C and D is changing, so C and D will not be there. So it is A bar, B bar, right? And for this, what you could have got, it is A B bar, right? And C and D, nothing will come. Now these two are been basically is A bar, B bar plus A B bar. So see, this is still not the minimized expression, because you can do a further simplification of this. If you take B bar common, it is A plus A bar, which is nothing but this B bar. So you see, after doing this Boolean algebraic, what you are getting this B bar, right? That the same thing you are also able to get from this Carnot map if you try to maximize the number of ones in a particular particular group, right? So it is true that when you are making this group, try to make the group as large as possible. Okay, but the only condition is that it should be a combination of either 2 ones, 4 ones, 8 ones, 16 ones, 32 ones, means 2 to the power n, right? 2 to the power n combinations you have to take. Is this clear? Yeah, please tell me, is
Yes,
this
sir.
clear? Okay, great. I think with this we can stop with Carnot map, and we can actually go ahead. Yeah. Okay, let me tell you one more thing. Suppose here in some Carnot map, okay, in some Carnot map, suppose in some position there is some one, okay, which you are not able to actually make a group of with any of the other ones, right? Then you have to write that term separately. Are you getting my point? Suppose here it will be difficult. For example, here also okay. Suppose in this earlier example, if there is an one here, right? So you cannot combine this one with any of these ones, right? So for this one, you should have written separately this A, B, and C, D, right? So this term will come like in addition to this separately, if you are not able to combine.
Sir, if we take the 0001 and 1001 together, so then we will get
00, which 00 you are saying? Could you
sir
please?
AB 00 and CD
Like this
01.
one, where I am pointing, and this one, or means there are two Carnot maps. So which one you are referring
Sir,
to?
the top one.
Okay.
So like you said, we will take the group of size 4 first, the
Uh-huh.
4 corner ones,
Mm-hmm.
then the blue one, and then we can take 0001 ABCD
0 0
01.
0 0 0 0 1. Okay.
Yes, sir. And 1001, the one in the same column at the bottom.
Same column at this bottom. Okay.
But sir, there we will get B bar, C bar, D.
B bar, C bar, D. But how you are reduced? Means no. I think I. Okay. Could you please repeat your question once again? I could not follow you.
So what will be the group
Huh.
if we take those two?
Which two? Okay, can you please point it out, like the values of A, B, and C and D?
Yes, sir. The ones, sir, those ones only. 0, 0, 0, 1. Yes, sir. That
Zero,
one.
0, 0, 0, 1.
0, 1.
Okay, so you want to
And
take this one and
one. Yes, sir. That one.
below this one.
Yes, yes,
One,
yes, sir.
1, 0, 0. So only these two.
Yes, sir.
Yeah, then that is not the minimized one, na? If you have taken this, right, that is not the minimized one. So again,
But sir, all ones are considered, no?
yeah, all ones are considered. That is true. So here also I was showing you, right? So if instead, if you could have, see, this is the minimized expression, right? Even if you are writing it in this way, then also suppose if you are considering this one as a separately, then that this term will come here, right? Now here also, if all the terms have been considered, no issue in that. But this is not the minimized expression, because here there is an opportunity for you to take a make this one and make a like no, take this one, make a group, and to do a further reduction of number of terms. Is this clear to you? So there are a couple of things. First thing is that you have to remember no one should left. You should consider all ones, right? And when you are making groups, you have to remember that try to make the groups as large as possible, with a consideration that the number of elements in a group, should be within this 2, 4, 8, 16, 32. And you should also consider where you can group. Like for example, Carnot map is foldable, considering that which what are the possible ways of grouping. We should consider that. Yeah, these are the only
And sir,
simple.
we have to minimize the number of groups, right?
Yes, you have to also minimize the number of groups, and that will automatically happen. When
Yes,
you
sir. Sir,
maximize
means
the number,
this way that I suggested, there will be only 3 groups.
there will be only 3 groups. So here also we have 3 groups only. See, that's what we are getting, the 3 terms.
Yes, sir. Means the 3 groups is the minimum that we can get, but in this way we will get like slightly different.
Right. So what you will be getting, okay, what you have suggested is this B bar C, B bar,
B bar.
B bar, D bar plus, okay, from here what you will get, here the value of A is changing, B is, it is B bar, and C is C bar, D, right? You are getting this.
Yes, sir. Like instead of the first term B bar C bar, we will get B bar C bar D. Rest everything will be the same.
No, I think I did a small mistake here while writing. I think you will not get this, because this term is because of these 4 ones, right? The red one, right? This one. This one is due to the green one. And so for this green one, you are,
So green ones will be the same.
1 minute. So, okay, first let me see that which groups you are considering, because otherwise it is like, now here so many groups are there. So let me redraw it here. CD 0001. Yes, now you have here 1, 1, 1, 1, 1, 1, 1. Yeah. Could you please now tell your groups which
Sir, the 4 corner ones, first of all.
4 corner one you want to make a group? Okay, fine. So this is gone. So from
Yes,
this,
sir.
which term you are getting? You are getting B bar, D bar, right?
B bar D bar.
Okay. Next,
Sir, then those two.
these two. These
Yes,
two
sir.
like this, or like this?
Yes, sir. Like that.
Okay, like this. Okay. So this is then what? This
B
is
C bar D. B C bar D.
no. It will it not be B bar?
B bar C bar D. Sorry.
B bar, C bar, D. Okay. Then
And sir, the ones,
this
those two
one and
ones.
These two ones.
Yes, sir.
Okay, so this would be which one? This is A bar, C D bar, isn't it?
Yes, sir. So, sir, what
Okay.
I'm saying is that when we look at these two expressions, they are looking slightly different, but
Right.
essentially they are the same. Like instead of B
Essentially,
bar, C
okay,
bar,
right. So
we have
suppose,
B bar, C bar, D.
right,
So,
see, these expression, the first one, these expression, like if like these are like all the expressions are same only. We are not changing this expression, but what we are doing is that we are minimizing the expression, right? So all the expressions are same. Only difference is that we are minimizing the expression. So here we can see, here we have we have an AND operation between these two, then AND operation between these two. But for your case, you see, AND operation first for these two is same, but here is an AND operation between three variables, no? So here basically three terms. Here basically you have two terms, right? So it will still further minimized. But eventually this and this and this, they are the same expression. That will give you the same function.
yes, sir. Thank you, sir.
Is it clear to you?
Yes, sir.
Okay. Yeah.
Sir,
Then, huh.
so finally we have to minimize the number of groups, and for each group we have to try to maximize the number of ones.
I think you tell the other way. First, try to make the groups which is as large as possible, right? When you are doing so, the other way, it will result the result would be the minimized number of groups only, right?
Okay.
And
And
when
sir,
when you are grouping, you have to make sure that no one has been left.
okay.
Okay.
And sir, can't we do like this? We do some combination of groups means,
Mm.
and after we get an expression, we try to use some Boolean algebra because that is already minimized. So we can always ensure that answer is correct.
Yeah, you can, if you want to do it that way, it's fine. But in many times it will be very hard to look at the particular expression and to tell using Boolean algebra how to minimize it. Okay, probably one of the example I will show you today.
Sir,
Hmm.
sir, suppose we have a 2 cross 2 Carnot map
Hmm.
whose entries are 0, 1 and 1, 0.
2 cross 2.
Yes, sir.
Okay, 2 cross 2 Carnot map whose entries are
0, 1 and 1, 0.
like here. I should write here 0.
Yes, sir.
0, 1,
1, 0.
1, 0. Yes.
Yes, sir. So what will be its Boolean expression?
Okay, let us do that. Can we make any group?
No, sir.
No,
We
sir.
cannot, right? Because to make a group we have to number 2, but like you cannot make a combine these two, because when you fold this, right, this 4 corners should also will come, right? Then here you have 0, so you cannot combine that. So here what will be the expression? The function would be, that's you cannot minimize it, so it will be A bar B, and here it will be A B bar. So basically it is A XOR B. So this is the function.
Sir.
Hmm.
Sir, now if we take A bar B as a Boolean number,
A bar B,
B
huh,
as a Boolean number X, okay? So,
as a
sir,
Boolean number X, okay. Hmm.
so sir, A B bar will be its complement.
A B bar will be its complement. Really? Let us see that. So A B. So now this is the function for you, right? And
Yes,
you want to make a complement of this, right? So let us try to do this. So it will be complement this. Now we know De Morgan's theorem. So it will be A bar bar plus B bar. So it is basically A plus B bar.
okay, sir.
So
I
this will
got
be
my mistake. Yes, sir.
fine. Okay.
Yes, sir.
Okay. So here we will do now some discussions on this NAND and NOR gates basically. Okay, and we'll see how useful these gates are. Okay. So this NAND and NOR gates actually together, like both of them, are called these universal gates. Right. Because any Boolean function can be implemented by either using NAND gate or using NOR gate. Right. So remember that any Boolean function can be implemented by using either AND gate, either NAND gate or NOR gate, right? So okay, so to implement any Boolean function, what are the like basic operation that that is coming to your mind? So couple of operations. For example, it is the AND operation, right? OR operation, NOT operation. So these are the basic operations, right? If you can able to do these three operations, then probably you will be able to implement any Boolean function using a particular gate, right? So let us see that whether this NAND gate can be used as a NAND gate, whether this NAND gate can be used as an OR gate, whether this NAND gate can be used as a NOT gate or not. Okay. So let us start with this NOT gate. Okay. So this is an NAND gate, right? It is like A, B, and this is the output, say this F. Okay. And its truth table is, oh, what am I writing? It is A and B. A, B, this is F, 0, 0, 0, 1, 1, 0, 1, 1. Yeah, I want these numbers from your side.
1, 1, 1, 0.
1, 1, 1, 0. Very good. Okay, let us now think in this way. If we short these two gate, okay, and make it so it is basically is the same, right? A equal to B, basically, right? Then what will be the function?
Not A.
Not
A complement.
A complement, because you can see from here, right? You see from here, right? So when this A and B both are 0, 0, where same, the output is 1, right? This is basically complement of that. Similarly, you can see from here, when this A and B like both are same and they are equal to 1, output is equal to 0. So basically it is the complement. So it is this A bar, right? Okay. So this is the NOT implementation using NAND gate. Now let us do think about this AND gate. So AND gate, A, B. So this is here. What will be the output?
1, 1, 1, 0.
Right. Okay. In terms of expression, can I write it like this?
Yes, sir.
Okay. So it is A, B. Right. Okay. So after this, if I use this one, will I not get this?
Yes, sir. You get it.
Okay. So is it not then the AND operation? And we are not using any AND gate, right? But we are using the NAND gate only, and we are getting this AND operation, isn't it? Okay. Now another basic operation, that is the OR operation. Okay. If I do it like this, what will be the output here? We know that. Please tell me what will be the output?
A complement.
A complement. Right. Here B complement. Right. Now can you tell me what will be the output here? So again, let us do it. So it is basically input is A bar and B bar, right? So it is A bar dot B bar. Then this is an NAND gate, so it will be whole bar, right? It is basically two input AND operation and then whole bar, right? Now we know De Morgan's So it will be A bar whole bar plus B bar again 1 more. So it is basically A plus B. Then please check, is it not the OR operation?
Yes, sir.
Yes, sir.
Right. So we can see that all three basic operations can be implemented by using only NAND gate, right? Similarly, you can use NOR gate to implement any of this basic operations, right? So now if you can implement this NOT gate, not operation, AND operation, OR operation using NAND gate, then if any function, any Boolean function, you should be able to implement it using using either NAND gate or NOT gate. Now here in this class, I am only showing the implementation using NAND gate, but I want to give this NOR implementation as a homework.
Sir,
Bolo?
sir, but why are we implementing these things with NAND gate? I mean, sir, AND gate is a single gate, and if we implement it using NAND gate, then we need two gates.
Right. You are very correct. But you know, other thing is like you need only one type of gate. You got my point?
Okay, sir. Yes, sir.
You need only one type of gate and implement, and a real fabrication of AND gate that way is bit easier.
Yes, sir.
NAND and NOR gate. Okay. So this is the thing now. So okay, please do this NOR implementation. It should not be very different from this NAND implementation. Just a small thing you have to change, right? But please do it, okay? NOR implementation as well.
So
Then
so can you say again why implementation through these will be easy?
see, first thing is that you need only one type of gate, right? You have suppose only NAND gate, so you should be able to implement it. You don't need any other gates, right? And the other one is like this in gate. You remember that like while we are doing this BJT, we have, I think, BJT or MOSFET. We have also studied like how to make NAND gate, NOR gate using BJT circuits or MOSFET circuits.
Yes.
Right. So this implementation of this, circuit implementation of this NAND and NOR gates are also easy.
So, but mostly we know, right, which gates need to be connected with which gates, and it's not like we use one particular gate for one function and then reuse it for some other function. So why is it necessary to have only one kind of gate? The chip will be designed only once, and we can use any gate we want. So in that way, instead of taking the space for 3 NAND gates, using just one OR gate would save us more space, right?
Yeah, you are right from that point of view, but also see, when you are when you have suppose multiple gates, right? For each gate you have different power consumption level. For each gate you have different delay and all these things, right? If you have a similar type of gate, then for design as well as for your hand calculation, it would be easier, right? For this gate, this is the delay. For this one, this much current drive it can handle. So all this would be similar.
Yes, sir. Okay, sir. Thank you.
Okay. So here I have a question now for you. Please implement the XOR operation using NAND gate. Remember XOR operation, that is A XOR B, right? Using NAND gate. Only NAND gate. Yeah. Can you please do it? So it stands for this A plus B is A bar B plus A B bar. This is the expression, right? Yeah, please let me know how you were thinking.
Sir.
Hmm.
Sir, we will start with A and B bar,
Hmm.
like using this one, using NAND gates only. We will convert this A into A bar and B as it is, and then go with the intersection. Like,
Okay.
can we use the intersection gate, sir?
Intersection gate means which gate?
Sir, AND gate.
Yeah, you can use obviously AND gate. No, AND gate means no, like you can use only here NAND gate.
Okay.
You cannot use any other gate.
Sir,
Huh.
sir, for calculating XOR, we
Hmm.
need not of A, not of B,
Hmm.
and we need AND of A bar and B, we need AND of A and B bar.
Hmm.
And we need OR of these two terms.
Hmm.
So we know all the three basic operations
Basic
using
operation. So from there you can do it, right? Yeah, and I understand. But then in that case, what will be the total number of NAND gates required? Can you just estimate it? Maybe I will.
10.
Yeah. How many?
10.
9.
9.
9.
Oh, 9. Right. Now let's see that we are doing one circuit and see that what is coming out of this particular circuit, if it is useful.
So we will be needing 7 gates, right?
7 gates. Okay. Your friends told me 9 gates. So yeah. So I do not know at this moment. So let us try it and see that what it is. How much gates we really, or how many gates we need actually. 1 minute. Huh? This is A, B. Yeah. Okay. Now, can we please check that if the circuit is something like this, then what will be its output? Let us check it. Okay. So here it is A is fine. So what will be the output here after this?
So
Sir, A and B.
Right. A, B bar, right? And here it is A. So what will be the output here? Please tell me.
A bar plus AB.
A bar plus AB. Okay, you have split it, right? Okay, fine. Right. Here it is B. Then please can you tell me what will be the output here? It will be
Sir, B bar plus AB.
B bar plus
B plus AB.
AB. Right. Okay. Good. Then after that, what will be the output here? So it will be A this one dot B bar A B then bar. Right. So can we then separate it out? It is A bar A B plus. Right. Okay. We can further do it, right? Do this. So it will become A bar dot AB bar. Please check, okay, and tell me if there is if your calculation is different from my calculation. Okay. So here it is this AB bar. Am I correct?
Yes, sir.
Okay. Then here it is A this one is B this one, isn't it? Okay. Then after that, what can we do? Probably we can again split it, right? So probably we can split it like this. This B, we can split it like this. So here A dot A bar is basically 0, right? It is A B bar. Again, B dot B bar is 0. So it is A bar B, right? So then it is basically this A XOR B, right? So we can see from here that by using a very small number of gates, this NAND gates, we can implement this XOR operation, isn't it?
Sir,
Huh.
sir, how you thought of this circuit?
I have not thought. This is a very like standard circuit. Okay, this is not my my contribution.
So if we are given any arbitrary expression to just means implement it
Right,
using the NAND
right.
gates,
Then
how
then
to think of
then yeah, yeah. Then what you can probably do, you can start with this. How to implement this NAND, NOT, and OR gate for that particular circuit using that. Okay.
so that might
Sir,
not be
is there any
optimal.
reduction? Sir, is there
Right.
any reduction method like two
Uh,
NAND in series?
very, very,
In series,
very.
we remove them.
Yes, very good, very good. Yeah. So that's one I want to discuss now. Okay. So suppose you have a particular circuit, but I will not make the circuit. But that is also given in your book, but probably I will not make it that big, because if I make it, or maybe can I? Okay, I have some time. Okay, no issue. So see, suppose you have given some function, okay, and the function, if you if you have implemented using this basic gates, basic gates means AND gate, OR gates, NOT gate, right? The function would look means the implementation is something like this. Okay, here it is B, and this output comes and connected with this AND gate. Here it is A, and this output is again been connected with F, right? And this is B, and this is C bar. Okay, so suppose a function has been given, okay, and if you have implemented that, if you want okay, what will be the function then? So here it will be like CD, and here it will be this B plus CD, like that, right? Then here it will be A into B plus CD, right? And then here it is BC bar, right? Here it is OR gate, so it will be this AB plus ACD plus BC bar, I guess. Is this correct? This expression, the final expression?
Yes, sir.
Okay.
Yes,
So
sir.
suppose then this is the expression that is given and you have to implement it. So, okay. So you can implement it first using the known gates, right? So these are the known gates, right? Right. Now you take each gate and replace these gates using this NAND design, right? Each of the gates. So let us then start and do it. So first it is this AND gate, right? So AND implementation, we know it is something like this, right? It is CD, and then followed by a NOT gate, not equivalent of this NAND, right? That would give you here this AND gate, or maybe for this, okay, I can use this one, this color, to indicate that this was one of the gate. Okay, then we have an OR gate. So for OR gate, we know what we have to do. We have this one, right? Then we have one more input. That input is here B, followed by we have one more NAND gate, all right? So this is for this OR gate. Okay. Then we have again this NAND gate. So for this NAND gate, again, this is A and followed by another this, right? So this is again this AND gate. So this is the third gate. Then we have a OR gate. So for OR gate, we know the implementation. This one, and this one, right? So we can say then this is this which OR gate? This OR gate, right? So let us say this 1, 2, 3, 4. 1, 2, 3, 4, right? Okay. Then we have here one more gate, which is this one. That is, here it is AND gate, right? And this output will be connected with this. So we have an AND gate here between this B, C bar, right? So here it is. I write it here, fifth, right? So this is the fifth gate, right? So this is actually, you can see just what I have done here. Just simply, just converted each and every logic operation using the NAND gate. So you can do the same thing using NOR gate as well. Once you know how to represent or how to get that OR operation and operation using NOR gate, right? Now, here one interesting thing is that you see from here. See here, this is okay. What is this? Okay. What is? Let me take this color. What is this gate?
The not
Means what is this? Sorry, not this gate. What is this? Is obviously NAND gate. What is this operation?
Not.
Not operation. What is this operation?
Not.
Not operation. Okay. Then suppose here, okay, by some means here the input is X. Then what will be the output here? X bar.
X bar.
Right. Okay. What will be the output here?
X.
X. So you can see what is the input here. The same thing you are getting here as an same, right? Same thing here, right? But unnecessary you are using in between two NAND gates, right? And it is basically not changing anything. It is, you are getting the same thing. So what you then can do is you can eliminate this one and this one from here. Do you agree with me?
Yes, sir.
Yes, sir.
Okay. Okay. Then let's try to find out if we have any other similar type of things or not here. So could you please help me in finding out?
So 3 and 4.
This one, right? This one and this one. Am I
Yes,
correct?
sir.
Okay. So these two also
Yes,
can
sir.
be eliminated. Okay. We can eliminate this. What else?
5 and 4.
Right. Right. So you can see we are able to eliminate 1, 2, 3, 4, 5, 6. 6 gates, right? And now we have left with this 1, 2, 3, 4, 5, 6. So is it 6? 1, 2, 3, 4, 5, 6. 6 gates. So we are able to eliminate at least half of the gates from here, right? Is it clear to all of you?
Yes, sir. Is there any other method to reduce further from here?
Oh, from here, like to further than that? No.
So can you explain this for XNOR gate, like starting with the end OR gates and again bringing to NAND gates, then reducing to the one which you drew.
Yeah, could you please check it whether you are getting the same thing or not?
Sir,
I am getting 5 gates by that.
5 gates, but here how many gates we have used? 4 gates. So what
Sir,
can we do? Then what can we do? Yes. So here, this type of circuit, but to design this type of circuit, you need, some experience here, right? Right, like how you will be getting, use minimized number of gates and really get the same operations. Okay. I think for the time being, let us not focus much on reducing from 5 to 4. But if you are able to do it in this process, okay, for the time being, our purpose is served. Okay, so but please remember here one thing again I want to mention: node implementation is as homework. Okay, so please do that node implementation. Right. So here we will do a couple of things. So here further, this NAND implementation. Right. Suppose a Boolean function is given in this way. A function of, okay, let me write that number of variables, that would be easier for you. So say a Boolean function, okay, where the variables are x, y, z, 3 variable function, is represented in sum of product form or sum of minterms form, and it is given as this 0,6. Right. So then can you quickly tell me what will be the terms if I want to write this in terms of x, y, and z?
Sir,
Hello.
A complement, B complement, C
A,
complement,
no. Here x, y, z, Baba.
X
A,
complement, Y complement, Z complement.
x complement, y complement, z complement. Very good. Plus
Plus
XYZ
XY,
complement.
Z complement.
x, y, z complement. Very good. Okay. So suppose you have given this, this function, and you have been asked just to implement this function using using this using this NAND gate. Okay. So what you can do then for this implementation is quite simple. Like this, you take an 3 input NAND gate, connect X bar, all these 3 inputs, Y bar, Z bar. Okay. Take another 3 input NAND gate, connect this 3 variable X, Y, Z bar, right? And then further take another NAND gate, and you will get the same function. It is quite easy to understand because from here what you will get is this X, Y bar, Z bar, then whole bar. Here we will get X, Y bar, Z bar, then whole bar. And here what you will get X bar, Y bar, Z bar, whole bar, like dot this X, Y, Z bar, this bar, and again bar. All right. So this bar and this will cancel out. So it will be X, Y bar, Z, X, Y, Z bar, isn't it? So the thing is that if any function is given in the this operations, this way, in a canonical form, and it is expressed in sum of product form, then you can directly use NAND gates to implement that particular function. Again, I am not saying that whether you will be able to minimize it or not after minimization. No. Suppose straightforward, you have to implement this function. Okay, then this is the implementation process. But for that, it has to be given in sum of product form for NAND implementation. Right? Okay. So here I have a question. Suppose we need to now have to find f dash, or if I am using this one, so let me be consistent in here. So x, y, z bar. Suppose I want to find the inverse function of this. So can anyone guide me? How should I do? And I have to use the same thing using this expression. Means I have to get implement it using this NAND gates only.
Sir, we can just add not gate at end of the first circuit.
We can get like after that here, right? After that here you are saying like you will be using like this.
Yes, sir.
Okay, right, you are right. Okay, so fine, right. Okay, see, but the other way would be also if you are thinking in this way, right? Is a 3 variable Carnot map. Okay, but what you said is correct. 0 0 0 1 1 1 1 0 0. So here the function f is 0 and 6, right? So this is 0. So here it is 1 and 6 is which one? 0, 1, 2, 3, 4, 5, 6, 7, right? So 6 is here. So these are the two ones, right? So the remaining things would be 0. Isn't it? Right. So in some case, if you have to implement, not in some case, means I think we have also discussed this quite earlier, right? If you have to find what is x bar from this, then what you can do, instead of taking this ones, you can combine these zeros, and that will give you the minimized expression for f dash, right? So if you're combining here zeros, how can we combine? Any idea how can we combine these zeros?
Group of 4.
Group of 4. So maybe probably can we think of this way? This is 1. Okay, what else?
Group of 2.
Group of 2. Which one you want me to do? Like this?
Yes, sir.
And like this? Okay.
Yes, sir.
Then what will be the this function for this 4? It is x is variable, y is variable. It is z, right? It is z plus. Okay, for this one, what is the function? X bar.
X bar y.
Y, very good. For this,
X y bar.
X y, very good, right? So you see, this is also in terms of sum of product, but it is not in the canonical form, but it is in the sum of product form. It is not in this type of fashion, right? This then inside plus and then multiplied, right? It is not in this form, right? Not in this form, but in this SOP form, it is like this plus, like in this form. So from here to you can directly use this NAND gates and implement this particular this inverse of this function. So how? See this here. This is x bar y. So what you can do here, x bar y. So we are assuming that the inverse functions are also available. So here it is x bar, it is y. Then here it is xy, xy bar, xy bar. And then we have a single function like single variable z. So but that z must go through and this NAND gate. Right? So this is another way by which you can implement this f dash. Now if we know f dash like you have done from here f to f dash, so here similarly if it is f dash, right, if you connect another not operation. So you will also get here F. Right? So there are a couple of ways by which you can implement. Right? But only thing you have to remember here is that for NAND implementation, it has to be in this sum of product form or in main term form, sum of main term form. Similarly,
Sir,
if
sir, can we use more than 3 input NAND gate?
we try to avoid it. Okay, there will be like maximum 3 variables only for your case, because there are something is called fan in and fan out. Maybe in the next class I will discuss that. Okay, that gives some restriction on what will be the maximum number of inputs that is possible for a particular gate. And also there is a maximum, suppose this output, right? See, this output is only fed to means this gate is output is fed to the input of this, right? It could have happened, right, that you could have made something like this. Suppose you need X bar, so you get this X bar, and this X bar you need for this up here, you need X bar for here, you need X bar for here, you need X bar for here, right? Then how many number of gates, similar type of gates you can attach to a particular output, that is also limited by the amount of current, okay, that this gate can supply, right? So this is called the fan out. What is the maximum number of gates you can attach to a particular gate, okay, for a reliable operations, okay? So that is also restricted, okay, how many gates. So better that we will take it as a maximum number as a input and output as a 3 to be on the safe side as of now.
Okay, sir.
Yes, but that is a very good question. Okay, now here is the NOR implementation. So for NOR implementation, what you have to do, you have to express that particular function in product of some form. Okay, for NOR implementation. For example, suppose a function is given. Okay, maybe let us take the same thing. Okay, same thing means let us take this function only. This function only. Huh? If as f x y z is 0 to 6. F x y z, it is summation of this 0 to 6, right? So it is given, and we have to been asked to represent it in the using NOR gate. But we know that for NOR implementation, we have to express it in terms of this which gate, in terms of in the product of some form, right? So here we have seen like earlier that f bar can be represented, okay, from this like this. So let me also write this, okay, that f bar that we have seen earlier only, we can write it as for this function, this, right? Okay. Now, if I take one more bar here, so that will give me f only, right? So here it will be the right. So now remove it. So once you remove it, what will happen? You can x and it become y bar, right? Then this De Morgan's, right? It is x bar y, isn't it? So the same function, which is this, can also be represented in this form. And see, this is basically POS form, right? So now you can directly use this NOR gates to implement this. So how? So here it is not difficult after that. So just directly use this x, y bar. It is x bar y. And okay, here there are only one input. There is. So it is this z bar, right? This. So this is F. If you want to check it out, then you can also do that. X plus Y bar whole bar. Here it is X bar plus Y whole bar. It is Z bar. See, it will be also Z bar bar. Huh? And here it will be X plus Y bar whole bar, right? Plus X bar Y whole bar plus Z bar. So I am writing it again Z, right? Again one more bar, right? So if you split this out, so it will become X plus Y bar. This bar goes, right? This become dot. So it is X bar Y, right? Then again this become dot and this becomes Z bar. So it basically see the same function.
Sir, is the last input Z bar in the NOR gate implementation?
It should be Z bar bar.
Okay.
2 times, na? It's basically the same as that of this NAND gate only.
Sir, the input for this NOR gate is Z or Z bar?
This is Z bar.
Okay, sir.
Okay, yes, you are right. Let me follow the same symbol. This is Z bar. Okay, and here it is Z bar bar. So basically it is basically nothing but a NOT operation. So I told you, like, do one of the homework. So one of the gate right now I am doing. So if you want to use NOT gate, if you want to implement NOT operation using NOR gate, so this will be the implementation. If you have doubt, so you can actually check it out. So for NOR gate, right, if these two are the inputs A, B, and this is the output F. So this is A, B, and this is output 0, 0, 0, 1, 1, 0, 1, 1. Yeah, could you please help me to fill this out? What will be this function? This here values for 0, 0?
1, 0, 0,
1,
1.
For 0, 0, output would be
1.
1.
1.
And here
All other
0.
All zeros.
all zeros. Okay, so let us now see that if you connect these two, means A or B and equal, right? So when A or B and equal and is this 0, output is 1. When A and B are equal and these inputs are then the input is 1, the output is 0, right? So basically then if you have a NOR gate and if you connect this, so that will give you the NOT operation. Is this clear?
Yes, sir.
Okay, very good. So now then we'll go towards the next section, which is the combinational logic. Okay, so this is combinational logic. Combinational logic means, like, we have studied, so for example, say like here, this particular circuit. Okay, we can generalize this particular circuit something like that. We have some gates, we have some inputs, right? We have a single output. So this is basically a combinational circuit. Okay, where if you change any of the input, right, its output might change, right? But this output is only dependent. Okay, here output is only dependent on the inputs, present state of the input, right? There is no feedback path from the output to input, right? So this type of circuits are called the combinational circuits. But if the time permits, we will also see there are some other circuits called the sequential circuits, where there is a feedback path that is present from this output to the input. Okay, so as there is a feedback, So the output then not only depends on the input state, but it also depends on the previous output. Okay, that is for the sequential circuit. But for combination logic circuit, it is the simple, this type of circuit. You have some gates, some inputs, and output. So this is the combination circuit. So there are different types of combination circuits. Okay, different for different purposes. So one of the purposes is just to add two single bits. Okay, that is called actually adder. So this adder can be also like divided, right? This adders can be also divided into two ways. One is called this half adder, and the other one is the full adder. Now, what is the difference between this half adder and full adder? So this is basically one, this single bit adder. Okay, so it's basically doing an addition for a single bit, like adding one with one or one with zero, like that. So what is then this half adder? So half adder is, suppose you have this adder, single bit adder. So here it takes only two inputs, say A and B, right, and gives two output. One is what is the sum and what is the carry, right? So it is taking only these two. Okay, let me first tell what is the full adder, and then it will be clear. Now it is so it is half adder. So for full adder, things are a bit only one thing has been changed. It will also generate sum and carry, but here we have an also input which is called carry from previous adder. Okay, so what it means is that something, say like we want to add two numbers. Okay, say this 1 0 1 0, or maybe 1. That would 1. Here we have to add with 1 0 1 0. Suppose we have to add these two, right? So here how many adders are required? This half adder or this full adder can add only one bit. So that way, if you want to do all this addition parallelly, then we need one for this, second second one for this, third one for this, fourth one for this. So we basically need then 4 adders if you want to do everything type of parallel, right? So here what is happening, see, for the first bit, right, or this is called the least significant bit, LSB, right? For the least significant bit, or which is at the almost at this extreme right? So we will add these two, right? It is like one, basically, like it is basically 1 1. Then it is the sum is 0. So right, sum is 0, carry is 1. So carry is 1. We have to put add this carry with this. So it is 1 0 is 1, right? Plus 1 with carry, that is our carry. Then 1 1 is 0. Right, carry is 1. So take this 1 here, right? Then 1 1 again 0, right? Carry is 1. So 1 1, then here 1 1 0, carry is 1. That carry will go and sit here. Now could you please check that what is the equivalent of this number, the first number?
11.
Is it 11? Yes, 8 3 11. What is the equivalent of this?
5.
5. And what is the equivalent of this?
16.
16. So is it matching?
Yes, sir.
It is matching, right? So here one thing probably you have noticed that for this least significant, to add these two least significant bit, we don't have any carry which is coming from the previous adder, right? So here we can use the half adder. We have only 2 bits that we have to add, A and B, right? However, if you consider from the here onwards, or maybe I can choose some different color. If you consider from here onwards, here you have to obviously use A and add A and B, right? Here you have to use add A and B. But at the same time, you have to also consider what is the carry that is coming from the previous adder, right? So this is the carry from the previous adder. So that part also you have to add, right? So that is basically the difference between the full adder and half adder. Is this part clear to you?
Yes, sir.
Okay. So then let us implement this half adder first. Half adder, right? So half adder, just writing it as in short HA. There are two variables, like not two variable, two bits that we want to add, and this output is sum denoted as S, and the other one is carry denoted as C, right? So then let us try to make the truth table. So truth table is the relation between input and output. So input is A and B, output is here sum and carry, right? So write all possible combinations of input. 0, 0. What will be the sum? Please tell me this thing.
0.
0. Carry?
0.
0. 1, 0. Sum?
1.
Carry?
0.
Very good. Next one.
Sum 0, carry 1.
Sum 0.
No, sir, sum is
No,
1.
sir.
Sum
Sum
should be
1,
1,
carry
sir.
0. Yes, sir. Yes, sir.
Sum would be 1, right? Yes. So sum 1, carry 0. Isn't it?
Yes, sir.
Okay. Next one.
Sum 0.
Sum is 0, carry 1.
Sum is 0. Carry is 1. Right? Okay. So let us see that, what is the function then? So this S is 1. Okay. For value of A0, B 1. So that means we can write it as A bar B, isn't it? And for this term, it is A B bar, right? We are writing in terms of this sum of product form or sum of min term, right? That's how we have written it earlier, right? So this is the sum, and so you can clearly see this is nothing but A XOR B, right? So what is carry? And we cannot further minimize it, right? What is C?
So you please explain how you got A bar B and AB bar directly from the truth table?
Oh, okay, okay. So here for this first for this one, right? So we are for this sum, okay, we have to write the function, okay, in terms of A and B. So here first we have to check where we are getting 1, right? So for the first one, that is this case, right? For this first one, okay, what is the input variable? Here it is A0, B1. So A0 means it become A bar. B1 means it is B. Do you have any difficulty understanding this? Because this is the same thing we have done for earlier.
No, sir. Yes, sir. Yes, sir.
Is it clear to you? Okay. So same thing we have done for here. This for this one, right? It is like A1, B0. So here it is like A is A, means A1 means it is A, B0 means it is become B bar, right? So that's how we are getting this A XOR B. Okay, is it clear, right? This is clear now? Is this clear, this sum?
Yes, sir.
Okay. So then what about carry? See, for carry, there is only one, here you can see only one in this column. So obviously there is no question of minimization. So you have to take this one, and that is for A and B, right? So it is carry is A and B. So as simple as it is. So what will be the then equivalent, what will be the circuit if you want to really make an half adder? So it is pretty simple. So take an XOR gate, right? Give here A and B, that will give you sum, right? Take this A, take this B, and use an AND gate, and that will give you carry. So as simple as it is, right? So this is basically a simple half adder circuit you can make.
Sir,
Hmm.
then at the last, sir, we also need to add this sum and carry, right?
Which one?
Sir, this sum that you have created right now and carry.
This sum, yeah, this sum we have to add with whom?
Carry.
Carry, why?
Sir, how we get, sir, a sum B?
A sum B means no, please, this is half adder. Okay, so this is half adder. Half adder is being used only for the least significant bit. So here is no carry which is coming from the previous adder. So you have to just add only these two bits.
Okay. Yes, sir.
Okay,
Okay.
so I think
Yes.
probably what we are mistaken with the next one. Next one is the full adder. Here we have to add this one with means this A, this B, with this B. At the same time, we have to also see what is the carry which is coming from here, right? From here.
Yes, sir.
Got my point? Okay.
Yes, sir.
Then let us go to the next page and try to do what is this full adder circuit. So full adder circuit. So full adder we have understood. Its block diagram is something like this. A, B, carry previous. These three are the inputs. Output is sum and carry. Right. So for that again, to draw any circuit, we have to first do the truth table, right? So it is X. Okay, it's not X, Y, Z. I'm writing. We're writing A, B, C. So we'll write A, B, C. A, B, C. Output is sum and carry. So write all possible combinations. So all 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Yeah, now please tell me what will be the values here. What will be the sum here?
0.
0.
Sir,
Carry?
0.
Carry?
0.
0. Next?
Sum 1, carry 0.
Next?
Sum 1, carry 0. Sum 0, carry 1. Sum 1, carry 0. Sum 0, carry 1. Sum 0, carry 1. Sum 1, carry 1.
Very good. Very good. I hope you have understood, right? This is simply just addition. If it is 1 plus 1, then it become 1, 0, right? So the sum becomes 0, carry become 1, right? So last one is 1 plus 1 plus 1. So 1 plus 1, so that become sum become 0, carry become 1. Then with this sum, we have to add one more 1, right? So it is 0 plus 1. So the sum is also 1, carry is already 1. So that's how it is coming. Okay, now let us use the Carnot map and see whether we can minimize these expressions or not, if possible. So here we have 3 variables. So it is a 3 variable Carnot map. So 8 boxes. A, B, C, 0, 1. So here it is 0, 1, 1, 0, then 1, 0, 0, 1. Could you please check, is this correct? This is for sum. Is this correct?
Yes, sir.
Okay. If this is correct, then we can also write what is the expression for sum? Yeah, can you please then tell me what is the expression? Can you minimize it?
No, sir.
No.
No, sir.
So then you have to write the individual terms, right? Okay, so let us start from here. It is 0, 0, 1. So it is A bar, B bar, C. Okay, next one is this. It is A bar, B, C bar. Next one is this. It is A, B bar, C bar. Plus, next one is this. It is A, B, C. Right? So you cannot minimize it. What can we do? So if I have to like if you have to now make and like circuit for this sum, like to get the sum, I think you can always do it like this, right? So you can take an AND gate, A bar, B bar, C, right? That will give you this. Then you take this A bar, B, C bar.
Sir, gates are AND gates. NAND gates are they are NAND gates, right?
No, this is AND gate. So here we are using only AND gate because it has not been asked to implement using NAND gate, no? A, B, C, right? Now after that simply add them. Now see we are using here four input OR gate. We have to, right? Otherwise what you can do, you can use first two, right? Then one more OR gate with first two, and then means I'm saying like you can add this first two term using an OR gate. You can add first these two terms using OR gate, then add them again using an OR gate. That is also possible. Like if you want to split this four, do not want to use it, use a 4 input OR gate. Then you can split it like this.
3+1, right? 3 input OR gate and one more 1 input OR gate.
That also you can use.
Yes.
Sir,
right?
Target. What does one input target mean?
One input means club 3 together and then take that output
I think
along
what
with
your I think what your friend is trying to
Then
mean. Yeah, something like this. Right? Are you trying to say like this?
Yes.
Okay. So I need to remove this part, so that I can write it here. Okay, so this part has been done. So now sum is some expression we have, the expression of sum. Then we have to find the expression for carry as well. So for carry again, again we have to do this K map and see whether we can minimize it. So it is A, B, C. So here it is 0, 0, 0, 1, then here 0, 1, 1, 1, right? Yes, here we can do couple of grouping. One group is like this, one is like this, the other one is like this, right? So this is for carry, right? So carry C can be written as this, okay, for this, right? For this it is AC. Oh, let me write carry because here also C is there, here also ABC carry is there. So let me write carry only. So it is AC plus this one is AB. This two group. From this two group it is BC. Right. So this is basically the expression for carry. Then if you have to implement the circuit for carry, it is also pretty straightforward, right? Use this three NAND gates, three AND gates, then followed by one OR gate, 3 input OR gate. So that way you will get this carry, right? It is AC, AB, this is BC, right? This is carry. So this is the expression for sum, circuit for sum, and this is the circuit for or carry for a full adder circuit, right? Is this part clear to you? Full adder.
Yes, sir.
Okay, then I have a question. The question is, now you know how to make half adder, right? Then I will ask, like, implement this full adder circuit, okay, using two half adder circuit. So again, I am repeating the question. Implement this full adder circuit using two half adder circuits.
So we can
Okay.
just add A and B using half adder, and then that input,
Huh.
like output of that, and one more half adder we can add there.
Okay. So here this was like half adder, what we have seen earlier, right? This was the half adder, this was sum, and this was carry. Sum was A, like A XOR B, carry was AB, right? And for full adder, this is for half adder, right? Whereas for this full adder, the expression of sum is bit different, right? What was the expression? Let me see it here and write it. What was the expression? Expression was like, yeah, can please anyone tell me that expression, sum expression?
Sir, A bar, B bar, C plus
Maybe I can copy it from, I can copy it from just a minute. Yeah, so this is the sum expression. Yeah, so I am just writing this as like sum for full adder. So for full adder, this is the sum. And what was the expression of carry? Carry expression was like AC, AB, BC. AC, AB, BC. AC, AB, BC, right? Is this right?
Yes, sir.
Okay. Yeah. Now, please tell me. What can we do? Isn't it? Right? This is a sum expression, right? Let us, try to do some manipulation here and see what can we do from here. So let us take this term. Okay, consider this term and consider this term. Okay, and let us say we will take C common. So it become A bar B bar plus AB, right? And from here, let us take C bar common, right? From here, this C bar common. So it will become this A bar B and AB bar, right? So this one we can write. This is what actually? This is what actually?
Sir, A bar XOR B.
A bar XOR B. And what is the inverse of XOR? What is the inverse of XOR?
XOR itself.
No idea? Why? Okay, let me let me come to this this part bit. Okay, bit just after a few seconds. Okay, so what is this one? This C bar. What is this? A bar B plus A B bar
XOR.
A is or B.
X or B. Bas, yeah, you know this part, right? Okay. Now it is A X or B. This is the function. So what is the truth table? 0 0 0 1 1 0 1 1. What is the truth table for this? X
0 1 1 0.
0 1 1 0. Okay. Now if this F is A X nor B, okay, then what is the truth table? Say this is F1. F1. What is the truth table? Okay, what is this function actually is? A, this one is A B bar, A bar, B bar plus AB. Okay, so maybe you can, from this function itself, you can tell me. For 0 0, what is the value?
1.
1. For 1 0?
0.
For 1 0 0. For 0 1?
0.
0. For 1 1?
1.
1. So you can see this, what is the relation between F and F dash? They are inverse function, right?
Yes.
Yes, yes.
So this one is this XOR, right? So this XOR can be written as, right? Okay. Now you consider it like this, that A XOR B, this as say X. Okay. So it becomes C X bar, C bar X, right? So this is again XOR. Is this part clear to you?
Yes, sir.
Yes, sir.
So is it clear to you now? The sum I can write in terms of like the sum of a full adder, I can write A XOR B plus XOR C.
Yes, sir.
Okay. And let us now also do a couple of manipulation for the carry. Okay. So the carry is here, this one. Carry is AC, AB, BC. Right. So what can we do with this carry? Or maybe before that, I think one thing we have understood, right? That we have to use two half adders to make a full adder, and here we have understood that it is basically A XOR B XOR C. So maybe we can just start, just get the sum right out of this half adder and see after that what we can, what else probably we can do.
Sir,
Bolo.
sir, the expression of sum we have derived from K map. Sir, we have assumed that it can't be simplified further.
Okay.
And sir, here you have reduced it into.
Really, have we reduced it?
Sir, I mean you have written small function.
No, small function, it is XOR function itself is a big function, right? Right. Whenever, if you are using suppose XOR gate, then you need less number of gates, right? You understand
Yes.
my point, right?
Yes,
But
sir.
it is XOR function itself is like A XOR B itself is in this A B bar plus like A bar B, right? Isn't it? This
Yes,
function
sir.
itself is big function. This is, we are doing it because for half adder circuit we have used this A XOR like XOR gate, right?
Okay, sir. Yes, sir.
right? So for this half adder, it is A, B. So this become A, XOR B, right? Now with this, we have to we need to add this C as well, na? So we will add here this C. So here it become A XOR B XOR C, and this is the sum of the full adder. So some part is been done, this part. And till here we have AB, right? And the carry is this, right? Here we have one more one more AND gate, right? We do not know what is the output input of this NAND gate, AND gate, right? We have an AND gate only, and probably we will make at max use one more OR gate to get the output. Okay, let me first I think complete the circuit, because the time is also not much today. So here what we can do is that we can simply take this, add it here. Okay, one of the this AB is being fed to here. Just a minute. I think no. How come we can feed this AB? Then it will be multiplied with some other term, na? But here we have only this AB, this type of term. So we will be taking this one AB directly. But what we have to do from here is that we will take this A bar like A XOR B, this thing here, right? And we will take this part we will take separately. We will take the another one is this, right? So here what we will get is this A XOR B and C. Then we will take this two with an OR gate sum up. So here we will get A XOR B into C plus AB, right, plus AB, and we have to show that this is nothing but this carry function. Yeah, this is nothing but the carry function. So can you prove it that this is nothing but this carry function?
Sir, if we introduce an OR gate, how is it in terms of a half adder circuit?
We have not introduced NOR gate. This is OR gate.
Yes, sir, OR only.
So we have used two half adder circuits. In addition to that, we have taken the help of one OR gate. Okay. Then you want me to mention it in the question? So I will do. I do mention in this question. What is happening? Half adder circuit using the full adder circuit using two half adder circuit and OR gate. Okay, so can you do it, or should I do? Like this term is actually this term. If we can show, then I think the design is complete. So
Yes,
maybe
sir, it can be shown.
it can be shown.
Yes,
How? How?
Sir, we first expand A's or B.
A's or
as
B, which is basically this, right? It is A B bar, right? And then we
AB.
will write this one as like this, isn't it?
Okay, sir, you have a different method.
Okay, and please let me know how have you done it.
Sir, I have multiplied C with
Right, you have this part. Okay, so what is x plus x? What is x plus x?
X.
X. means x or x actually, plus we are saying like while we were talking using plus. Okay, then if we add one more, then also it will become x only, na?
Yes, sir.
So this is ABC. So I will use this one here. So I will write ABC 3 times. Okay. So I have written ABC 3 times, right? So I will take now individual terms, right? For example, this one ABC. From here I will take BC common. So it become A bar. Then I will take this and this as like these two, and take probably like AC common, and that will give me B bar and B. Then I will take like from these two AB common, that will give me C plus C bar, right? So here you can see this term is 1, this term is 1, this term is 1. So that will end up with this BC, AC, AB, right? And let's see that what was the carry for the full adder. It is AC, AB, BC, right? So this one is nothing but the carry of the full adder. So this circuit uses two half adder circuit, and one, and in addition to that we are using one OR gate to get the to get a full adder circuit, right? So is this part clear to you, or if you have any doubt here? Yeah, any doubt? I am not getting any response from your side. Any doubt?
No, sir, it's clear, sir.
No, sir. Clear.
Okay, and it's easy only, right? It's some simple manipulation only, right? Okay, so I think it's around 10. So we'll stop here today. So we'll meet on, I think tomorrow. Tomorrow is holiday, right? Tomorrow is holiday, right? Hello.
Yes, sir.
Yes.
Okay. Yes. So we'll meet
Sir?
again on the next week. Yes.
Sir, can we add the two carries by using the half adder instead of using OR?
Can we add two carries? Which two carries? Like you are saying this is one carry and this is the other carry, these two?
Yes, sir. The two ANDs which you have done after that, if we use a half adder instead of OR.
Half adder here.
Means no, means like the sum, means the XOR gate.
We have not used XOR gate. We have used here XOR gate. XOR gate. Okay. Okay, XOR gate. Yeah, right. I am right. But I do not understand one thing. Like this part is this part. How can we change? This part is the full half adder part, na? What is your question? Can you please repeat?
Sir, actually, I'm not getting your voice properly. Actually, there is some net problem here, sir.
Oh, okay. So is it clear now? Better or?
Yes, sir.
Okay. So actually, what is your question?
Sir, question is that if we just don't, it means like at the last we have used an OR gate to finish the carry part. So there we can use a XOR gate instead of OR gate.
There we can use an XOR gate. Okay. Will the XOR gate will give you the carry? Have you checked it?
Sir, because the carries will be means even if we add them, there will be no carryover of the carries. Like both of them cannot be one. Only one of them can be one at most. So even if we use a XOR gate, I think we should get one if like we should get the
Okay.
desired output.
Okay, that you think, right? So could you please check it as well using a pen and paper and tell me in the next class?
Yes, sir.
Okay, so please do a check. Huh? Okay, then thank you very much for attending today's class. So, and I wish you a happy Diwali. Okay.
Happy Diwali, sir.
Happy Diwali, sir. Happy Diwali, sir.
Yes. Thank you. Thank you
Happy
very
Diwali.
much.
Happy Diwali, sir.
Happy Diwali, sir.
Yeah. Thank you. Thank you very much.